Calorimetry is the process that we use to determine or to quantify amount of heat that can be released or absorbed during a physical change or during a chemical reaction. So there are several types of calorimetry, and I'm giving you the definition for two of them, and then we're going to um, go over one of those two types more in depth. So the first type of calorimetry that we're going over is constant volume calorimetry or bomb calorimetry. So for this one, you just need to know the definition of what it is. So this type of calorimetry we use to determine the heat of a reaction. So it's a constant volume. Okay, so when the volume is constant, we can actually determine like the heat of a reaction using a bomb calorimeter, which is the name of the instrument that we use to with this type of calorimetry. So basically, when we are using a bomb calorimeter, we can actually determine how much heat it's been released from a combustion reaction. So combustion reactions, if you have a compound containing carbon undergoing a combustion reaction, your products are carbon dioxide, water, and energy. So we can determine that specific amount of energy that is being released from a combustion reaction using a bomb calorimeter. And another application for this type of calorimetry is to determine the amount of calories that food contain. So now the second type of calorimetry is constant pressure calorimetry. And this is the one that if you're taking a lab for this class, you are going to be doing an experiment using a constant pressure calorimeter. Constant pressure calorimetry, it's also known as coffee cup calorimetry because we can actually use a coffee cup as the calorimeter or the instrument that we use to determine that amount of heat that it's being transferred. So in the picture, what I have here in this picture is just how a setup for an experimental procedure looks like. So if you're using constant pressure calorimetry, and it's constant pressure because that's just atmospheric pressure, you will have a coffee cup, and we usually have two of them. Okay, so we have one coffee cup inside of the other, and the coffee cups are made of an insulator material. So it's styrofoam. So that type of material will help the actual heat that is being transferred to remain inside of what you have in the coffee cup. So it's covered, you have a solution in there, and what we use to determine like heat transfer, it's a thermometer. So with the thermometer, we're actually looking at changes in temperature. So I'm going to go over two specific examples for this constant pressure calorimetry. When we're looking at constant pressure calorimetry, it's pressure at atmospheric pressure, so that's why the pressure is constant. Enthalpy is the same as heat at constant pressure. So when we're actually doing an experiment using constant pressure calorimetry, what we can determine with the information, experimental information, is the enthalpy change for a physical or a chemical process. So my first example here is just a physical change. I'm dissolving a solid in water, preparing a solution. So that's just a physical change. So I'm going over the problem to check what we need to find out and to check the information that it's given. Ammonium nitrate, it's what it's been dissolved in water to prepare your solution. So ammonium nitrate is the solute, and now the problem is telling you that the solution becomes cold. Okay? It means that you have an initial temperature, and that temperature is decreasing. You're given a specific amount for ammonium nitrate. You're given a specific amount of water, which is the solvent. You have a temperature here, 24.9, and you have another temperature. So your initial temperature is 24.9, and the problem is telling you that that temperature decreases to 20.3. So I'm going to identify my temperatures. This is my initial temperature. This is my final temperature. Now you need to calculate enthalpy. So enthalpy is heat. The enthalpy value that you're trying to calculate here needs to have units of kilojoules per mole of ammonium nitrate. So when we're calculating enthalpy, we can follow steps specifically with this type of problem. I'm going to write down our equation. So we're using the equation for heat. So to solve this equation, to find out amount of heat, you need the mass, you need specific heat, and you need the change in temperature. The change in temperature we can calculate. I already identified the temperatures. You have Ti 24.9, your final temperature 20.3. Now for the mass, you have a mass of ammonium nitrate, which is your solute. You have a mass of water. So when you're dissolving ammonium nitrate in water, you're forming a solution. That's what's happening. A solution has two components, the solute and the solvent. Solute plus solvent is equal to your solution. So if you want to determine that mass, to plug in a number in that equation, you need to determine the mass of your solution. So if your solution are composed of your solute, which is the ammonium nitrate, and you have 3.21 grams of that one, and the solvent, which is water, and you have 50 grams of that one, the mass of your solution is going to be given by the addition of the mass of your solute plus the mass of the solvent. So the mass 3.21 grams of ammonium nitrate plus 50 grams of water. That's going to give you the mass of the solution. Now, if you check the problem is not giving you a value for specific heat. Usually you have a number that you can plug in, or the problem will tell you assume that the specific heat for the solution is the same as water. Since the information for specific heat was not given on the problem, we're going to do the calculations assuming that the specific heat for the solution is equal to 4.184, which is the specific heat for water. So I'm going to put a note. No kilojoules, that's joules, grams over Celsius. So delta T is the final is 20.3 and the initial is 24.9. So that will give you a negative number, 20.3 minus 24.9, negative 4.6 Celsius. So we're calculating here the heat of the solution. 53.21 times 4.184. Since the temperature is decreasing, right? You have the final 20.3, the initial was 24.9. You have a negative change in temperature, negative 4.6. So when you solve this 53.21 times 4.184, which is the specific heat for water, times that negative delta T, you're going to get a negative number. The units are canceling out besides joules. So that number is amount of heat in joules. So we're not done with the calculation, but I want to go over some things using this problem here as an example. This problem here, it's representing the dissolution of a solid in water. So you have an ionic solid right there, ammonium nitrate. So there are bonds that are holding together your two polyatomic ions. For your compound to actually dissolve in water, that bond that is holding together your ions, it has to be broken. Okay? Your solid needs to be broken down into the ions in order for that compound to dissolve in water. Okay? So for that attraction between your ions to be broken, it requires energy. It needs to absorb energy. It's an endothermic process. That that bond needs to absorb energy in order for your ions to separate and actually dissolve in the water. The amount of energy that it's required for those ions to separate, it's coming from the surroundings. The system in this specific example here is the dissolution of your ammonium nitrate in water. That's what you're looking at. Everything that is in contact with your dissolution, with your compound, it's going to be the surroundings. So your compound needs to absorb heat from the surroundings in order for the ions to separate. You see how the temperature is decreasing. The temperature that you're measuring is not the temperature for that bond that it's being broken for you to get the ions in solution. That's something microscopic. The temperature that it's being measured is the temperature for the solution, which is surrounding that physical change that it's happening. So your compound is absorbing heat from the solution. That's why the temperature that you're measuring goes down. So absorbing heat, the temperature goes down and you get to feel something becoming colder when your process, what you're looking at, it's actually absorbing heat. It's absorbing heat, it's removing the heat from the surroundings or the solution in this case, which is the temperature that you're determining. So that temperature change right there, going down, it's decreasing because your compound it's absorbing heat to actually dissolve in water. So I have this specific problem here, ammonium nitrate, is the compound that you have in cold packs. Right? So you have the solid and you have a pouch of water, and when that pouch of water breaks down, it gets mixed with your ammonium nitrate, and that will feel cold because your ammonium nitrate will absorb heat from your solution to actually dissolve in the water, and that's the temperature will decrease and you get to feel the pack very cold. Now in the second picture, in the circle, I have my system, what you're looking at. Okay, in this case that represents your ammonium nitrate. Now you're measuring the temperature of the solution, everything that is around your solution. So this temperature that you're measuring for the solution, the temperature for the solution decreasing means that the process that you're looking at, it's endothermic. The actual system, it's absorbing heat. Since the system is absorbing heat from the surroundings, your system, what you're looking at, it's endothermic. Absorbing heat from the surroundings means that the temperature of your surroundings, which in this case is the solution, will be decreasing. The opposite is also true. If you have a system that is exothermic, the exothermic system will be releasing heat that goes into the solution, and now the temperature for the solution will be increasing. So back to our calculation, because we're not done yet. Okay? The problem is asking you to find enthalpy or change in enthalpy. Not the enthalpy of the solution, but actually the change in enthalpy. So we have a numerical value right there, which is heat, and we have a negative number. Now we need to find out the enthalpy. So enthalpy, it's represented like that. So if you want your enthalpy in, the only thing that you need to do is divide the value of the heat that we already calculated by the number of moles. So the problem is asking you to find kilojoules per mole of ammonium nitrate. So we have to find out the moles of ammonium nitrate. You're given an amount of ammonium nitrate in grams, 3.21 grams of ammonium nitrate. And to convert the grams of ammonium nitrate to moles, you have to divide by the molar mass. So the molar mass of ammonium nitrate is not given, but we can calculate that. It's nitrogen is 14, each hydrogen it's 1, and then you have 3 oxygens, each one is 16. That should give you about 80 grams per mole of ammonium nitrate. So calculating moles, I'm going to put here. So 3.21 grams the molar mass, it's 80 grams per mole, so we're dividing the grams the given grams by the molar mass, and that's going to give you the number of moles. Grams are canceling out, so we're calculating moles. So we have that part right there. Since we want to calculate that change in enthalpy in kilojoules per mole, I'm going to write down my heat Q in kilojoules, which is just dividing that number by 1,000. We're moving the decimal place 3 times to the left, divided by the number of moles that we calculated. That sign does not go there. Kilojoules per mole. So something very important here. You see, we're calculating Q first. Mass times Cs times delta T. That number for Q, it's a negative number because your temperature is decreasing. That's the temperature for the solution. Now, when we're calculating the delta H, we're using Q, right? Again, the Q that we just calculated. In the Q that we calculated divided by the number of moles, because the problem is asking you to find enthalpy in kilojoules per mole of ammonium nitrate. You see, the negative number, I don't have my negative number in that last calculation. I don't have the negative number because this process here, the dissolution of ammonium nitrate, it's actually endothermic. Is the opposite sign of what you're calculating for the solution. For your solution, you have a negative number because the temperature is decreasing. So the temperature is decreasing, but because actually that process is endothermic and it's absorbing heat from your solution. So whenever you're trying to find out the enthalpy, the first thing that you're finding is the heat, and the Q that you're using to find out the enthalpy will always have the opposite sign of the one that you're using from your solution. Okay? So the heat for your solution has a negative sign. The heat that we're using to find out that enthalpy value will be a positive number. If you have a positive sign for the change in enthalpy, then that initial amount of heat that you're calculating will be a positive number. And then the heat that you're plugging in into the equation to find out delta H will have a negative number. Okay, so it's the opposite of what we already did in this problem. So here I'm going to review again those changes in the signs. So we're looking at heat transfer again, but now in chemical reactions. So remember, we did a physical change, which is just dissolving a solid in water. You can have heat transfer from a piece of metal that is at a higher temperature, and you can place that in water and there will be a heat transfer. We can use a calorimeter to determine that change in temperature and calculate everything or amount of heat that is being transferred in a similar way. So to go over like an actual amount of heat transfer using a chemical reaction, I'm using a neutralization reaction. Okay? So I have the example in the next page. So I want to go over again this exothermic. So we know that the change in enthalpy, right? Delta H can be positive or negative. If you have a positive sign, that means that that reaction, in this case, a chemical reaction, it's endothermic for your delta H. Okay? So if delta H is positive, that's representing an endothermic reaction. If you have a delta H value with a negative sign, that represents an exothermic reaction. So for endothermic, the reaction is absorbing heat from your solution. For exothermic, the reaction is releasing heat into the solution. Remember, the reaction is your system. And the solution where the reaction is happening, that will be your surroundings. So there's an exchange of heat between your system and the surroundings. System being the reaction and the surroundings being your solution. So I have two beakers with a solution inside, and I have reaction, which is representing the system. So for an endothermic reaction, that reaction is going to be absorbing heat. So the arrows are pointing towards where the heat is going. So the heat is going into the reaction. So the reaction is absorbing heat from the solution, which is the surroundings, and that amount of heat is going into the reaction. So when that happens, if you're measuring a temperature, that temperature corresponds to the temperature of your solution. So if the reaction is absorbing heat from your solution, the temperature of the solution will be decreasing, which is what happened in the previous example. The temperature decreased. Okay? It means that that process is absorbing heat from the solution, and that's why the temperature is decreasing. So when you have an endothermic reaction, the temperature of the solution will decrease. Now for an exothermic reaction, when you have a delta H with a negative sign, the reaction is the one that is releasing heat. Remember, exothermic is releasing, endothermic is absorbing. So your reaction is releasing heat, and that heat is going into the solution. So if you're measuring the temperature of your solution, you have an initial temperature. When the reaction happens, heat is being released, going into the solution, and now that initial temperature will go up because your solution will be absorbing that amount of heat that the reaction is releasing. So the temperature for the solution, if you have an exothermic reaction, the temperature of the solution will be increasing. So for endothermic reactions, the final temperature of your solution will be smaller than the initial temperature. So you do have a negative sign for that change in temperature for the heat of the solution. Okay? Your reaction is absorbing heat. Okay? So that heat is going into the reaction. So for the exothermic, you have a final temperature that is higher than the initial temperature because your reaction is releasing heat that is going into the solutions. So the arrows here are pointing from the reaction towards the solution. So the heat is being transferred from your exothermic reaction into the solution. And we can calculate enthalpy delta H for a reaction. Using our equation for heat. If we want to calculate delta H for a reaction, the experimental data that we can determine, that's the only thing that we can determine with this constant calorimetry. It's a temperature change. That's our experimental data. How the temperature is changing after your reaction happens. If it's increasing or decreasing. So our experimental data, it's a number of temperature for the solution. So we can calculate the heat of a solution. If your solution is absorbing or releasing heat. If your solution is absorbing heat, that heat is coming from the reaction. If your solution is releasing heat, it's because your reaction is absorbing that heat. Remember, the heat is being transferred from point 1 to point 2. We're assuming that there's no escape of that amount of heat anywhere else. It's not going into the calorimeter, just from heat exchange between the reaction or system and the surroundings or the solution. So the first thing that we are going to be doing is calculating amount of heat for your solution. The second thing, we're going to write down the amount of heat for the reaction Rxn. So the heat of the reaction is the same numerical value as the heat for the solution. Remember, if the heat is being transferred from one place to another, the amount of heat has to be the same. So what we use is just the opposite sign. If one of them is absorbing, the other one is releasing. So if your reaction is releasing heat, the solution is absorbing heat. So releasing will have a negative sign, absorbing will have a positive sign. So the Q for your reaction or the heat of the reaction will be the opposite of what you're calculating for your solution. If you're calculating a numerical number that has a negative sign for your solution, then for the reaction you have the negative of a negative number, which is going to give you a positive. If you calculate the heat of your solution and you get a positive number, then the heat of your reaction will be the negative of a positive number, which is going to give you a negative number. So the heat of the reaction is always the opposite of what you have for the heat of your solution. And finally, we can calculate the delta H or change in enthalpy for the reaction. If you know how much is the heat of the reaction, then you can divide that number by moles, and that will give you a numerical value for the enthalpy in joules or kilojoules per mole for a specific reaction. So I have one example, and these three steps here are the ones that we're doing in this calculation. So we're calculating enthalpy change in kilojoules per mole, and that will be mole of the acid. So let's go over the problem. It's a little bit different from the calculation that we did before, because in the previous calculation, all of the numbers were given in grams. So when you were calculating the mass of the solution, right, to plug in that number in the equation, you were just adding the masses for your solute and the solvent, and that gave you the total mass of the solution. In this example here, we don't have masses, you have volumes. You're mixing 250 milliliters of sodium hydroxide with 250 milliliters of hydrochloric acid. So the first thing that we're trying to do is to calculate the heat of the solution. Your equation is mass times Cs times delta T. So we need to find the mass of the solution. So to find the mass of the solution when you're given volumes, the first thing, you're mixing those two in the same calorimeter, okay? So when you're mixing those two volumes in the same calorimeter, then you have now a total volume. So we're finding the total volume, which is just adding the two volumes that you're given together. 250 for the base, 250 for the acid, that will give you a total of 500 milliliters. So if you have a volume and you need mass, what we have to do is to multiply a volume times a density. Volume times density will give you a numerical value with units of grams. If you go through your problem there at the end, you have that the specific heat and density of the solution is 3.74 and 1.25 grams per milliliter respectively, which means that if you have a total volume times the density of your solution, you can calculate the mass of your solution. So density times volume, your unit for milliliter cancels out and you get a number in grams. (500) times 1.25, which is the density, that gives you 625. So looking at the equation, I have the mass, you have the Cs right there in your problem. Now, another different thing is that in the previous problem, you were given a final and an initial temperature. So final minus initial, it's what you were using to calculate the delta T. Another way for you to find the change in temperature in a problem is like what you have in this one. This problem is telling you the temperature of the solution increased by 7.80. So it's not giving you an initial and a final temperature. It's actually telling you, okay, I had an initial temperature and that temperature increased by 7.80, which means that that 7.80 is by how much the temperature changed. And it's a positive number because it's telling you that it's increasing. So I'm going to plug in my numbers here. 625 is the mass. Then you have 3.74 joules over grams times Celsius for the CS. And then the delta T, it's a positive number. If the problem tells you the chemical reaction decreases the temperature of the solution by 7.80, it means that that change in temperature, it's a negative number. If the temperature is decreasing, that temperature change, it's a negative number. So I have all the numbers that I need to find out the heat of the solution, and that will be a positive number because the temperature of the solution is increasing. So 625 times 3.74 times 7.80. The units are canceling out, grams with grams, your Celsius here, and you're getting a number that is in joules. Now the problem is asking you to find the enthalpy change in kilojoules per mole. So I'm not going to write down the number, well, I'm going to write down the number in joules, but you need to convert that number to kilojoules. So I have my number in joules and in kilojoules right there. So that's my number one. Number two is to find the actual heat for the reaction. So the heat for the solution is a positive number. The solution is actually absorbing heat because the temperature of your solution is increasing. So that amount of heat that your solution is absorbing, it's coming from the reaction, which means that if you have a heat for the solution with a positive number, the heat for the reaction will be the same amount but with a negative number. The actual reaction is exothermic. The reaction is releasing heat that is going into the solution, and the temperature of the solution will be increasing. So one last thing, we're calculating delta H in kilojoules per mole, and we already have the kilojoules, but we need to find out the moles of the acid. So kilojoules per mole of acid to find out the moles of HCl. Let's see what information do we have. We have 250 milliliters of 0.125 molar HCl. So you have a volume and a concentration. .125 molar, capital letter M, is the same as 0.125 moles per liter. That right there, it's molarity, capital letter M. So if you have 0.125 moles per liter and you multiply that concentration times a volume in liters, which is this amount right here, that will give you the moles, because your unit for volume is canceling out, and what is not canceling out is unit of mole. So 0.125 times 0.250, those are the moles for HCl. So what I'm doing to find the moles of the acid, which is what you need to find out the value of the delta H, is just multiplying the concentration times the volume in liters. So one last thing, 18.2 divided by 0.03125 kilojoules per mole, and that's a negative sign right there. So this reaction, this neutralization reaction between sodium hydroxide and hydrochloric acid is an exothermic reaction. It's releasing heat, that's why you have a delta H that is a negative number, releasing heat that goes into the solution, and that's why the temperature of the solution increases.